All right, I went ahead and started the recording, so we'll start our meeting. I noticed that most of you are muted yourself, but feel free to unmute if you want to ask a question, or if you want to ask a question through the chat head, I'll keep that open too. So either way. Just to make it clear, the announcement that I made earlier, basically what we're going to do right now is go over the lab portion of the course. And for the lecture portion for today, we're going to I just had you watch the lecture from a year ago. The lecture portion didn't have any changes, but I did make a few changes just today regarding the lab portion of the course. Not into what's actually due, but instead I made changes to make it a little bit easier. I took out some of the processing steps, the early processing steps, and I'll show what I did. And then I also changed it so that you're downloading a whole ArcGIS project, and you just have to open that project up, and all the data is already loaded, so you don't have to load the data yourself. I'll probably make small adjustments like that to the remainder of the labs because that'll keep the time that we meet for the labs down. In the future, right now the goal is to get a faster internet connection at home and continue to do both the lecture and the labs live. But if that doesn't work out, then I'll move to a situation where it'll be like this week, where the lecture is a pre-recorded version, and then we'll meet together. And if anybody has any questions on the labs, I can answer them then. So today I imagine that I'll be talking for about an hour about how to do the lab. I'll try to do a lot of this week's lab right on the right here in Skype, and then I'll leave you to answer some of the kind of the more thinking questions about it. There is, in addition to watching the videos for today's class, there is a reading, and the reading comes from a textbook, so that it is all found on Canvas. So the reading, the Burroughs reading, and the videos from last week. And in the announcement, there's about I just didn't want to confuse anybody, because the first 3 or 4 minutes of the video I say, hey, there's no class next week, but remember, that's me a year ago. So we are meeting in our next week. So don't watch those 3 minutes, because I'm just kind of explaining no class next week, and I'm doing some housekeeping stuff. So start at about 3 minutes and 40 seconds in, watch the rest of that video, and then the other video, watch from the beginning to about, I forgot what it is, but it's an hour or so in, and then you don't need to watch the lab, because that's what we're doing right now, and I'm making the lab, I'm streamlining the lab a little bit. Okay? All right, so I downloaded the link. So the new fresh link, if you go to Canvas, what's that? Oops. Old password. Yeah. Okay, so if you go to this week's course material, and you want to work on this lab, you would download the information here in Lab 7, Spatial Interpolation. The reading is here. It's Chapter 6 out of a textbook. Then the lecture PowerPoint's here if you want to have that for your notes. And then the video links that I'm referring to, these are the video links from last time I taught the course. And I'll add today, this material, to this page as well. All right. So if you go into Lab 7 here and you click the data and text for this lab, it'll download, and you'll have a zip file. And that zip file might be in downloads by default, but you can move it to wherever you want. Right. So once you have it, you need to click into it wherever you stored it on disk. You need to right click, and you need to copy it out of there or extract it and then paste it here. Another option, if you right click on it and just say extract all, if you do this, I would remove this part of it. Otherwise it'll create a directory called, wherever you put it, ctemp. I'm putting in ctemp sa, but it'll call it ctemp sa/ex7/ex7. But that is an option. So I can hit this, and it's telling me, do you want to replace them? Because I already have them. Sure, I'll replace them. So now I have that directory. I notice that it doesn't have the little zipper by it, so it is extracted. I mean, at this point I could delete this if I wanted to, because I can always re-download it, right? So I'm going to double click in there, and then the next thing you need to do, you need to work with these two files for the most part. This is the text of the lab, EX7, and then this is the ArcGIS Pro project. So I'm going to double click that, and it'll open up, and it'll take me into ArcGIS Pro, and all the data for the lab will be loaded. So when you open it, it should look something like this. Okay? So the previous text of the lab had you add these data sets yourself, and they were actually named slightly different. I renamed them to be more clear. And it also didn't have a spatial version of this soil pollution points. So we'll talk about that in a second. Okay. I'm going to open up the document. All right, so this is the lab document. I'm trying to make this as big as possible. View full page. Okay. So this is the this is the text of the lab. Okay. So we already did this. Okay. Open up the ArcGIS Pro project file. And you'll notice that there is a standalone table called soil pollution.table. Okay. It contains the Burrow and McDonald soil pollution data. So this data is actually the data that was for that textbook. Okay. And by default, I'll show this to you here. I'll go back into ArcGIS Pro. By default, let's look at this soil pollution table. If we open it, you probably already did something like this in a course, but by default this is just a table, and it contains two fields that can be used to plot the X and the Y locations. So that's what these two fields are right here. So a lot of coordinate systems operate using the terms easting and northing, but really they mean X and Y, right? Easting would be X, northing would be Y. And so we can convert these coordinates into a point shapefile or a point layer, which is what I've already done. But if you want to see how I did that, you can actually, I'm pretty sure this will work for everybody. But maybe it won't, but I'll just show you here. So if you go to an analysis history, it should show you all of the tools that I ran to get here. But anyway, it's this XY table to point is the tool that I ran. So even if you couldn't see it in history, you could go into the toolbox and run that and open up this tool, and you get the same window. But this will show you the same parameters that I used to get there. Okay. So I'm taking the soil pollution table and I'm going to convert it into a layer called soil pollution points. And I'm going to use the easting field as my X field and the Y field as my the northern field as my Y field. And there's no Z field. The Z field means that the points themselves would actually be in a third dimension, high and low. Okay, but they're not. We're going to create a statistical surface that will have highs and lows, but we're going to do that as a next step. And so choosing a Z field here doesn't make a statistical surface. It only takes the points and gives them a 3D value so that you could look at them in 3D. That might be an interesting thing to do sometime. Now, if you chose one of these, like if you chose one of these pollution layers like mercury, and you ran it, then you could insert a new 3D local scene, and you could see the elevation. It wouldn't really be the elevation; it would be the amount of pollution extruded as 3D. Okay. But that's not what we're going to do today. All right, so I'm just going to leave that blank. And again, you don't even actually have to do this because I've already done it. And so if I press run here, it's just going to overwrite this file, which is fine. Now, the last thing here is the coordinate system. You do need to specify a coordinate system when you convert a XY table to point. Otherwise, it'll just put it, out in the middle of the Atlantic Ocean where 0, 0 occurs. And it'll be in reference to that, the intersection of the equator and the prime meridian. So here, the best way to do this, by default, it's gonna be like this, okay. But which is latitude, longitude. So what you can do is you can drop down. You can choose one of the other data sets that's already in the right coordinate system. That's the way I usually do it. So I chose, to just choose. You could choose any of these. I'm going to choose the landmass polygon. See how then it changed it to the same coordinate system that it was in, which places it somewhere in northern South America, okay, northern Brazil. All right, so I'm going to just hit run, and it's not really going to do anything because it's all just going to overwrite that one layer that's already there. So as soon as it's done, then the layer's back. Okay. So in the original lab, I said we're going to do that in class together. So I was just showing you how to do that in class together. Okay. All right, so I'm going to X this table out, and I'm going to open up the soil pollutions points. And you'll see that there's the exact same information there. Okay, exact same information. But now there's also a shape field that gives us the X and Y position. That's why it's displayed as a map, or as a layer on the map. And then we have all of the other attributes. So we do have an elevation field. We have a northing field. We have I'm not actually sure what this field is, the Deep River field. But then we have a number of different pollutants that are that have been sampled at these locations. So we know the cadmium content in parts per million, the mercury content in parts per million, the lead content in parts per million, and the zinc content in parts per million. And finally, the percent organic matter, which isn't really a pollutant, but it can be an indication of there being conditions for organic matter to explode into water and things that are growing in the water because the water isn't clean or isn't pure. So that's what that is. Okay. Then you have another couple fields, flood frequency and soil type, which are exactly what they what they say they are. Okay, so our task is going to be to interpolate the values within this study area. So I have this landmass polygon I'm going to turn off. So our study area is actually this area right here. That's what we mean by the landmass. So that is the study area for the project. It basically follows this ridge line here. And the data here isn't as the underlying data isn't as detailed, but you can see there's a little ridge line that runs along there. So we're going to take this data and we're going to interpolate what's underneath. I'm going to turn this one off too. So basically we just have a study area polygon. A study area raster, and we have these points, and we want to make a continuous surface with those points in that area. I know that probably not everybody's had time to watch the video, but in the video I demonstrated this in the United States with some weather stations. This is a much smaller area, but the same concept applies, where we're going to take these points and interpolate one of these layers. Okay. All right. One of these fields. Sorry, one of these fields. Cadmium, mercury. You choose it. I'm going to just choose the no, wait. What did I say in the? I forget which one they did in the article. Oh, anything but zinc. So you can't choose zinc because they already chose that. Okay. All right. So let's talk about the assignment now. Right. So the assignment is that we are going to reproduce this table. Okay. This table here from the Burroughs and McDonald reading. We're only going to create 3 fields. We're gonna find the minimum value and the maximum value for zinc within our study area, and then we're going to find the percent area that's greater than some cutoff value, and we're going to choose that value after we run one model. Okay. So sorry. So what we want to do is pick out a number of interpolation techniques. The idea here is to show you that there are a lot of different interpolation algorithms out there, and they do produce different results. And I want to give you guys a feel for how they look on screen, because cartographically, there is a reason sometimes to choose a interpolation algorithm because it looks better, because it's better cartographically. They produce different results. Sometimes they're smoother, and if we want to smooth our data more, we'll pick different parameters. And so I just want you to experiment with using different interpolation techniques so you can get a feel for some of the parameters that will change as you do so. Okay. And so the assignment here is that I want you to build a table kind of like I've built at the end of the lab here. This is something that I added. So my table looks kind of like the Burroughs and McDonald table, except for it only has 4 columns. And you are going to do at least one IDW. You can do more. Okay? You can do another IDW. And then I want you to do, up here, I want you to run it so that you'll do 1 spline interpolation and 2 Kriging interpolators, and then 1 other. I guess that's actually 1, 2, 3, 4. That's 5. Okay. So I've got that. And the 1 other can be an additional IDW. It could be an additional spline. It could be an additional Kriging operation. All right. So you're going to fill out the table with the data that you came up with. Okay. All right. And that then let's demonstrate this. And we'll fill out our table a little bit. Okay. Because that's what you have to do for the lab. All right. So in order to do these are all, if we go to Analysis, Toolbox, or Tools, toolboxes. And you go down to spatial analysis, spatial analyst tools. You can go to one of the tool sets is actually called interpolation. And so you expand that one, and you'll see that there are a number of interpolation algorithms. We talked about several of these, or I talked about several of these in the video. Actually, I talked about everything here except for topo to raster, which deals more with taking it's not strictly just interpolation. It's taking existing points, lines, and polygons that already represent elevation and converting them to a raster. Okay, but we talked about all these other ones, or I talked about all these other ones in the video. Okay. So go back and watch the video. And you'll learn about the how these are each done. All right, so let's start with IDW, since that's what I put is the first one in the table. Okay. I'm going to double click that, and then sorry, just backed up into something. Okay, so here you're going to choose your input point features. Now your input point features are going to be these soil pollution points. Okay. So these are going to be the points that determine the surface. The surface that we're going to create is for this entire area that right now you see is black. Okay. There are a few points outside of that black area, and they will be used in the interpolation. In other words, you know, just this will be a spoiler alert for the video for those of you who haven't seen it. But what we're trying to do is come up with an estimation of the Z value, which we're going to go ahead and choose. I'm going to choose the lead Z value. So so we're going to try to come up with an estimate of what the lead is everywhere here in the black. So for the value right here, it's likely that we want to consider this point to give us a value here, along with this point and this point. Okay. So the parameters that we choose for our IDW will influence whether or not we choose these points, or what points are chosen for each particular point, or each particular grid cell. So what all of the interpolator tools do is they go cell by cell and they guess at the value for, in this case, lead or whatever we've chosen. They guess for that value based on the surrounding known values. So I've got my lead parts per million, and the output raster is, I'm going to call that IDW1. Okay. Because I'm probably going to do another IDW. All right, now this other thing right here, the output cell size, don't set that here. Go into environments. I talked about this in the lab. Go into environments and change the processing extent to landmass polygon. Change the cell size to same as landmass. Sorry. I should say landmass raster, not landmass polygon. So the extent should be landmass raster. The cell size should be landmass raster. The mask should be landmass raster. And the snap raster should be landmass raster. If I do this, my output will be exactly the same size, and it will contain no data everywhere that this data set contains no data. So in other words, it won't be extrapolating. It won't be trying to figure out what the zinc value is way out here. Okay. So in environments, set all four: extent, cell size, mask, and snap raster. I went over that here. Okay, right up here. So you should use this layer in the environments options to set the mask, snap raster, cell size, and extent raster. Okay. We really aren't going to use these other two layers unless you want to like experiment with them. Okay. All right, so I have all that information there. I can go back to parameters if I like. So these are the parameters that explain how the interpolation is going to be done, because IDW looks for nearby. So let's say it's going to interpolate this cell's values. Well, it's going to look for nearby points. What defines what a nearby point is? That's here under search radius. Okay. So if I leave it variable, which is probably the more common option, that's why it's the default, what it's going to do is it's going to choose the nearest 12 points to come up with a value at that point. Right? And then the power is how much it will weight nearby points versus far away points. So the higher the power, the more it's going to weight nearby points, and the more it's going to punish points that are further away. That's what inverse distance weighting means. So it's going to raise the distance to the power, the inverse distance, sorry, to the power of this number. And when a number is below 0, you get, and the more you raise it to a power, the more you multiply it by itself, actually the smaller it gets. Okay, so that's why as you raise this power, the points that are further away will be less considered. Let's just leave the defaults here for a second. So the power of 2, the number of points 12. Okay, and we don't have any barrier features to worry about. We're just gonna say 2 and 12, and assuming that we've made all the environment adjustments that I talked about, then it's time to go ahead and run it. I'm going to close this, make it bigger so we can see the whole thing. Okay, so I'm going to run that. So when it's done, this is what you get. You get a interpolated surface. So this surface represents the amount of zinc at every single cell value. See what I'm saying? All right. Now, I'm going to do something real quick. I mean, sorry, not zinc, lead. We did lead. The authors did zinc. Okay, so I'm going to choose elevation, which is right here. And I'm just going to call this IDW elev. You could do elev if you want. I mean, you could do elevation if you want. I said, zinc, whatever. I said do one of the pollutions, but you could really do any one of them, I guess. So I'm going to run this real quick just to show you how this is different. Okay. So this actually is an interpolated surface of elevation. These are the higher values. These are the lower values. Okay. All right. So this is actually just over the ridgeline, it appears, going down into that valley. Okay. All right, so there's the elevation data set. Okay. Now watch what happens if I change the number of points that I want to use. I only want to use 3 points instead of the nearest 12 points. So I'll just call this elevation 3 and run it. Okay. See how it became more jagged and more abrupt in places, not as smooth. With almost all interpolators, that's the trade-off in their parameters. There is some parameter where you're smoothing the surface more than you would be if you adjust the parameter. But sometimes you're moving the parameter up versus moving the parameter down to get that result. Now also, if we changed the power to 5, let's see what happens. Run that. And I guess I talked about a lot of this in the video, but you could see how now we changed the power to 5, and it changed in a different way. It changed in that it's still some abrupt changes, but there's a lot less detail because the closer points are being weighted more, and so there's less interpolation being done, and it's more like a nearest neighbor because we're punishing the points that are further away, so it's weighting more heavily the closer point. Okay. All right, these two elevation ones, I'm gonna remove these for now because we're not actually doing that. We're gonna do the. Oh, did I accidentally read it? I thought oh yeah, anyway, I removed 3. So this IDW1 that I created, which is an interpolation of the lead field. Okay, that one is the one that we're going to use to fill out our table. Okay, so if you remember, we just did the defaults, which was 2 and 12 for the powers, for the power and the number of points. This is getting into the lecture part, but the other option here is the fixed. In other words, instead of choosing the nearest X number of points, we're saying all the points within a certain distance. Okay. The disadvantage to this, and I'll go ahead and run this real quick, is if we change the distance to something that's really small. I'm going to go with 5 here. Then what happens is that if there is no point, let's turn this off. See, there's 5 is a really small. Yeah, so 5 is too small. Let's do 50 and see, because it doesn't look. Yeah. So you see how there's just a bunch of circles, okay? Because in very few places in this raster was there a cell that was more than, was there a known value that was more than 50 units away? So right in here there was. So these values are mixed between these two known values. But everywhere else, all these are just saying, oh, well, the value is the same as that value, okay, and so on. So it looks like there was a little bit of mixing there. Okay. All right, I'm going to delete that one too. Okay. All right, so let's finally get into answering the question. Sorry. All right, so this IDW1 is the one we ran for lead. And we just called it IDW1. And so we want to fill out the table that's down here. And so let's just make a little note here that we used the fixed, we used variable, and power was 2, and number of points was 12. Okay, so that's what I meant here by the method and parameters. There is another parameter here, but it doesn't have anything to do with the way the interpolation's done. It's just the polyline features, and we're just going to ignore that. Okay. All right. So we need to find the minimum value and the maximum value and the value over x. So first we need to define what x is going to be. And because we didn't know beforehand, but now we do know the range of values. So we know that the range is going to go from about 60 on the low end for lead all the way up to about 653 for lead. Okay? So we just need to pick something towards the middle of that range. So what could we pick? Well, 100 falls nicely toward the middle of that range. So let's say the value is over 100. Okay, it's actually the percent. It's the percent of values over 100. I think that's what I said. The percent area. Well, the percent of cells and the percent of area is the same. Okay, so the percent of cells or values turns out to the percent of area over, and we're going to choose 100. Okay. Right. So these are pretty easy to calculate, the minimum value and the maximum value. In fact, ArcGIS a few years back, I think, put those values in the properties. So if you right-click on the layer and say Properties, and then if you look in the metadata, not the metadata, maybe it's general. No, source. Okay, source, and then raster information. The statistics. There it is. Sorry. You can get the values. So here's the minimum value. There's the maximum value. Let's just report these to 2 decimal places. So I'm going to take my minimum value and put it right there, and my maximum value and put it right here. And then I will have filled out the information for that, for those two. Okay. How do I get the percent of? I'll change this to percent of area, but it's going to work out. If it's percent of cells, that's actually what that's how I'm going to get it. Percent of area over 100. In other words, what I want to do, if I click this cell, the value is 76. If I click on this cell down here, the value is 428. I want to find out how much is over 100. And I am going to have to run a raster operation in order to do that. How could I make a raster where I have all of the values that are above a certain value classified as either a 1 or 0, and then all the values that are above a certain value classified as a 1 or 0? How could I do that? Anybody got any ideas?
Didn't we use something just like that like 3 weeks ago?
We've done something like that several times in the course.
The conditional operator?
The conditional operator would work for sure, yep. That's what I was thinking of, is using the conditional operator. You could also do it in map algebra using the conditional operator. And then a third way is we did it using the reclassify by table. Reclassify by values. So all three of those would work. I'm going to use the, I'll use the conditional operator. Okay, so I'm going to go to con, and then I'm going to input the IDW1, and then I'm going to enter my new expression, and I'm going to say value is, did I say greater than or less than? I know I've been saying over. Make sure I was consistent here. Yep. Percent area, oh, I wasn't consistent, less than x. And then I wrote greater than over x. Let's just leave it. Let's just leave the table consistent. Okay. Everybody's going to get different answers, so I'm obviously not grading on the answers because some people might be choosing zinc or whatever, or you can choose. Some people might choose cadmium or whatever. You could choose lead. There's no reason that you can't. So we're going to say is greater than. Really, since we only have two classes, 1 and 0, it won't really matter. It'll just be the inverse. So in other words, if 50%, sorry, that's a bad one. If 40% is under 100, then 60% is over 100, right? So, all right. So so here we just need to enter 1 and 0. So what this is going to do is going to go through every cell and determine if it's greater than 100. If it's greater than 100, it's going to give it a value of 1. If it's less than 100, it's going to give it a value of 0. So I will rename this con IDW1. Yeah, I'll just call it con IDW1, and then run that guy. I'm not sure yet if we've actually done it using the con tool like this in this class, but we have done the map algebra raster calculator where we said con IDW greater than 100, comma 1, comma 0. I'll just call this IDW or con IDW 2 or 1 alt. Okay, I just want to show you this would produce the exact same result. So you see how the color is different because ArcGIS just chooses random colors, but they're the exact same result. The exact same cells are colored 1 and 0. Okay, so it's the same tool that's being run. I mean, it's inside of the computer, it's the exact same programming code that is running in both cases. So I'll go ahead and remove that though. Okay, so we've got this. So how do we calculate the percent area over 100? In other words, the ones. Well, it's pretty simple actually. If we look at the attribute table, you could see that we have the number of cells that are both ones and zeros. Okay. So all you'd have to do here to make sure that you're choosing the right ones is just remember which ones you coded 1 and which ones you coded 0. We coded the ones that were greater than 100 as 1. So how could we calculate the percent of those values that are over 100? If we know that the ones that are over 100 are 16,275, and we know that the count, the ones that are not coded that way are 13719. How do we count the percent that are this category?
You just divide by the total area?
Yeah, so we could take the total of these two values, the count for 0 and the count for 1, and then use that as the denominator, and the numerator would just be that value. Okay, so I could do that in calculator. So 16. Well, here first I'm gonna So first I'm gonna add that to 13719. Okay, so that's the total number of cells. You're probably not going to get anything significant if you just round that to 30,000 because you're only off by 6 cells. Okay, but if you want to remember 2994, you can. Okay, so now we're going to go 16275, and then for the rest of the table, this will always be 29994. So 54% of the area is greater than 100. So you plop that over here, and you say 54. I'll round it to 2 decimal places, so it's 26. 54.26%, or you could say 0.5426. Okay. All right, so let's do another one. I said you could do IDW, so let's just do another IDW, and we'll change the power a little bit. Change the power to 3, and the number of points. Well, I mean, you can do whatever you want. I'm gonna go crazy and say 20 points. Okay. All right. So this should make a relatively well. It's only going to use the nearest. It's going to use the nearest 20 points. So there'll be a lot more points being averaged. So that should make it smoother. But I'm going to punish the points that are further away more and not weight them as much. So the overall value may be may still be a little bit abrupt, but it will it won't have as, I don't know if there's a scientific word for this, but it won't have as many jagged edges, but it may be more abrupt. Okay. All right. So turn this off for a second, and actually turn this one off. And if I want, I can go back to history. And the advantage of doing it this way, go back to history and go back to your IDW, the first IDW that I ran, is that all the parameters and all the environments will still be the same, so you don't have to reset all those. Okay. So you can go to parameters, and here I said I was going to do 3 and 20. Okay. And then I'll call this IDW2 since this will be my second IDW, and all the other parameters can remain the same. And I'll run it. Now let's compare them. So I'll turn this one back on and turn on and off for a second. You see? Yeah, go ahead.
How do you get the history at the bottom?
Okay, so if you go under the analysis tab up here, it's probably a lag. There was a lag yesterday when I taught my other course, but see under the analysis tab up top? See where I'm moving my mouse right now? Mm-hmm. And then history is right here.
So how do you pin it to the bottom?
Pin it to the, you mean like pin it as a tab?
Yes.
Well, it'll be there as long as you don't close it. See how I could go back to there and then I can go over to history?
So when I click on that button, it only shows up in the catalog.
It only shows up where?
In the catalog. Oh, well, maybe that's because I didn't update mine yet.
I'm not sure, but do you see the history? If you do hit history, does it come up?
Yeah, I see it.
Okay. Now, if you actually want to, like, if you hit this pin button, it'll go away every time you move, but I don't want to do that. I kind of like it staying open. Like if you hit this pin button, it disappears, and then you. I mean, if you like it better that way, that's fine. But I like to. I just like to leave it open on my screen. All right. Okay, so now you'll notice that if I toggle between these two, it's kind of like what I said. Choosing the 20. Oops. I'm gonna hit save here. It almost looked like it was going to freeze on me. Going to 20 points made it a more smooth surface because considering more points, and using a power of 3 removed a lot of these are what I'm talking about, these jagged edges, because it's not considering as many points locally. So that's the difference. It's a much smoother surface. The second IDW that we ran, and it has less jagged edges. Right? So let's see how it affected those other values. Right? I'm going to close this. And I can simply get the minimum and maximum by going under Properties and going to Statistics. And then here's the minimum value. Oh, remember, I'm only going to get 2 decimal places. So it's actually 37.00. Even though it looks significantly different, there was a relatively small change to the minimum the value, and an even smaller change to the maximum value, right? Well, no, sorry, that is. See, 0.2. No. So this is a very, very small change, and this is a greater change, but still very, very similar. So overall, there wasn't much change. You won't see that with every single one that you do. Oh, by the way, I'm going to put that we did lead here. Okay. All right, so I did those two. Let's see about the area over 100. So again, I can go back to the con tool, and instead of choosing in my history, instead of choosing IDW1, I could choose IDW2. And I could save it as con IDW2 and run that. And if I do that, I've got that same value. I mean the same, not the same value, the same same table. And you can see this time it's 15,235. And I don't have to calculate that other number again because it's the exact same number of cells. So just go back to my calculator and say 15,235. Divide that by 29994. And this time I got 50.79%. Like if I multiply this by 100. Take that back over here. And say 50.79%. So that actually changed significantly, a lot more than these other two. So the minimum and maximum value hardly changed at all, but the area over 100 did change quite significantly. Okay. I realize we're getting pretty close to an hour, but let's do one more. And then I'll talk about the rest of the deliverables for the lab. So I mentioned that you're going to do a spline. So we'll do that one next. I'll write spline right here, and then when it comes up, we'll talk about the parameters. Okay. So here we go. So under Tools, under Interpolation, I'm going to hit Spline. And here, you do have to enter all the parameters again because we've never done that yet for this spline tool. So you're going to have to enter your parameters and your environments. We're going to choose to do the soil pollution points again. We need to remember to keep using the same variable. So stay on lead if you're going to choose lead like I did. And then we'll just call this spline _1. And then we're going to talk about this in just a second, but before we do, let's go back to the environments, change the extent to landmass raster, the cell size to landmass raster, the mask to landmass raster, and the snap raster to landmass raster. Okay. So we're changing each of these so that we get the exact same cell size, extent, and everything. So there'll still be 29,994 pixels in our output, our cells in our output polygon. I mean our output data set. All right, so for the spline type here, you do have several choices as to whether or not you want to do regularized retention. You can experiment a bit. Okay, go back and watch the lecture, or even read about it. You can hit this little button, and it will. Well, that's not that descriptive, but basically, to sum up, a spoiler alert for the lecture, the spline method was created in the old days. They actually had like metal rulers that they would use to be able to draw curved lines through points, and so the line would change based on how stiff the ruler was. If the ruler was really stiff, then it wouldn't be a smooth transition between the points, whereas if the ruler was really bendy, you'd have more smooth transition through them. Okay, so anyway, that's how it works, and you can definitely read more about it here. And so it's a model of that type of environment that's fitting basically a smooth surface through the points. Okay. So if we change this to tension, which is more like what I described, then it's going to consider a certain number of points. And the more points you choose, the more it's trying to fit that flat surface that it's modeling through all of the points. And then the weight, kind of like the IDW weight, determines how much it weights the point values. but it is trying to model a metal sheet being put through all the points, a bendable metal sheet through all the points. Okay. All right, so I'm just going to leave it on tension 0.1 and number of points, and then run it. Okay. So that's the result. You can see that on average, the spline interpolation has very few abrupt changes in it. That's just one of its characteristics, because it's trying to bend that metal sheet through all the points, and it won't. Well, the virtual metal sheet through all the points. It won't make abrupt values until you get your number of points significantly, pretty small. Okay. All right, so that looks a lot smoother than any of the other, the IDW, tools that we did. Sorry. Save. See that? A lot more smooth, and it looks pretty significantly different. Okay, so let's fill out the table for this one. I'm going to say tension. I'm going to say weight 0.1 and number of points 12. Okay, just to report. Okay, then I go back over here, and notice that the range is a lot different. So we should see some different values there under statistics. So the lowest now is actually negative 12.03. That's a lot different.
Dr. Reber?
Yeah.
Are we supposed to be getting the same numbers?
If you chose the same exact parameters, you should be getting pretty similar numbers.
Okay, so it's okay if it's off by a little. So I noticed on my second one with the power of 3 and 20, my percentage came out to be 49.8. So it's off by about 1%. And I noticed that the attribute tables, my numbers were slightly different than yours.
Yeah, I wouldn't worry about it. There's probably some little difference that we did. But as long as your patterns are the same, that's what's really that's what you're really supposed to be learning from the lab, not the exact numbers.
Okay.
Yep. So did this go down for you between these two?
So let's see. On the second one, I got 37.00. So I got the max and min the same. It's just the percent. I got 49.79.
Okay. But what I'm trying to say is, in row 1, was the area over 100 the same?
Yeah, so if you look at the attribute table in yours versus mine for IDW2, my 0 count is 15,057, and my 1 count is 14,937. So it's a little bit different than yours.
Right. I'm just saying, you see where my mouse is right now?
Yeah.
Was that number higher than this number still for you?
Let me see. I didn't actually calculate that one.
Oh, okay.
So I got 54.26. Yeah, so I got the same as you.
Oh, okay. Okay. Yeah. Well, as long as it's going down, that's fine, because you're seeing the same pattern. So, I mean, if you want it, we can work through that together sometime and figure out exactly why it's different. But it's.
I mean, it's gonna be fine. I was just wondering. It might also be the fact that I haven't upgraded to the newest.
It could be that because of the number, if the count is slightly off, that it might have just done the interpolation slightly different.
Okay.
All right. Since it is an interpolation, you know, there's no right answer, right? Like, one of the things I talked about in the lab, I mean in the lecture, is that sometimes it's best to like withhold some points and find out how well it's doing overall. And then there's also the kriging technique, which will actually do that for you as part of what it does. Is it creates a statistical a standard error map, which will show you how far off it thinks it is in various places. Okay, so just the final part here is that I'm going to do the last thing on that table, which is the conditional tool again. And this time I'm going to change this to spline 1 and change this to con spline 1. And then run that. And notice that is a lot different than that. Okay. And so I would say, you know, I'm sure there's exceptions to this in some areas that you could better model with a gently undulating surface. Basically, it's a local trend surface. If you could better undulate, like maybe either some rolling hills or something, spline might do better than IDW. Okay, but in general, spline is going to be better for making a pretty map, a cartographically pleasing map, but not necessarily the most accurate map. It depends a lot on the conditions. Or it could be that, you know, we're not even talking about elevation. It could be something that we're trying to, like it could be that if we're trying to interpolate values that we sampled from a lake, from water, that because of the conditions of water, doing the spline interpolation works better. Okay, I mean these are all like questions that you could study, let's say. So the reason why there are different interpolation algorithms is because people have noticed that some perform better in different conditions than others, in different areas or different applications. So, so when you're faced with the problem, sometimes it's good to kind of experiment and see which one is doing the best, or go back and read some literature on it. But anyway, let's answer that fill out the last one. So 1's now 13,682. So that's going to be significantly different. Calculator. 13,682 divided by 2,9994. And we get 45.61 or 62, if I round that right. All right. So I've filled out the table. You're welcome. You know, because of conditions, you're welcome. Originally, I did zinc. I just like the book authors to show those, and I told you not to do zinc. But now you're welcome to continue working on this table and just do the last 2 rows on your own. Okay. So that is where you need to do that. Okay. There are several other things that you need to do on your lab. So you're going to make a small report. A paragraph's fine, but for sure less than 1 page on what you see. So don't write a whole bunch. So you're going to look at where the differences between each of these maps that you've made are large versus where they're small. Okay. So for example, that might be near the river. So, well, the river is not on this map, but it is on the north side of this. It's right here. It's right through here. It's not really a river, I guess, but the stream. So then the north side of that area coming through, I think it actually starts here, comes down through that stream that comes down there. Okay, so then the north side. So are there more differences on the north side? Well, the north west side, or are there more differences down here where there are less points? Okay, things like that. In a particular flood class, I did include the flood classes for you. So I'll just move that up to the top here. So here's the flood class. So the highest flood classes are the ones down by the river and the lowest areas, and then the purple here is the second highest flood risk, and the three are the highest areas, the ones with the least flood risk. So does there seem to be a pattern with flood risk and basically the variability that you get in the different interpolation algorithms that you've chosen? Okay. So just make some comment on the spatial location, and then you could highlight these in the graphic. So I know we're not teaching. We're not using ArcGIS Pro in your earlier GIS courses yet, so you may not have covered how to make a map in ArcGIS Pro, and I'm not really going to go through that. There are resources online to do that. Maybe I can provide some links if somebody wants. But for this lab, I'm going to accept it. If you just hit the Windows key on your button and you type in snipping, then you can basically snip a map out like that. Okay, and you could take that and you could copy that right into Word. So you can go down. Oops, I didn't want to do that in the table. So see, now I have that map in Word, and I could write something about it. Okay. All right, but just to get you started, if you do want to create a layout, you can go to Insert, New, and then you can decide what size you want it to be. You go to Letter, and then you can insert a map frame that you're looking at. So here I've stuck a map frame on. Okay, I can I can zoom. One of the tricks here is that you have to right-click. No, not right-click. Yeah, you can right-click. You have to right-click on this map frame and say Activate if you want to change the extent. In other words, if I want to zoom in on the actual map there, I have to do that. Okay, and then I have to hit this button, or I go back to the layout to deactivate it. Okay. And this allows you to make a proper map. It's good practice. You know, if you want to do this, you can insert a scale bar. You can insert a north arrow. These are all things that we teach in introductory GIS classes or cartography classes. Okay. So, but I'm waiving those requirements. You don't have to do this. Once you get the map the way you want it, you can simply export this layout. Yeah, I think you go to Share. Yep, go to Share, and then you export it. And then this is the export dialog. This tells you where it's going to save it. So I could call this, IDW1.jpg. So it's under Documents, ArcGIS. Yeah, okay. So then I hit export. Actually, this is actually spline, but you get the idea. So I exported that, and then inside of Word, I could say insert, and insert a picture, and I can go to the directory where it was. Right, what did I say it was? See, I think it was under Documents, ArcGIS. Yep, there it is. So I just need to see where I put it, and then insert that. So now I have a proper map inside of my Word document. Okay. So this is, it's definitely a good skill to develop, to be able to create something like this. You know, you can put this in PowerPoint or Word, or you can put it on a web page, whatever. You've got the ability to export that document, but you can do either way, whether you cut and paste it from a print screen, which is what I did. First one here is a print screen. Second one here is I exported it to create a new map. Okay. All right.
Dr. Raber.
Yeah, go ahead.
The maps you want, do you want the condition maps, or do you want the spline 1 map?
Yeah, I was just going to actually talk about that. So what I want is for the maps to support. What I want is for the maps to support your argument as to whether or not sorry, not your argument. Your paragraph that describes where there's the most change between the different sets. So it might actually be better to do the to do these, okay? To do these maps, because they will show where the big differences are occurring. Now, originally I had it written in the lab that what I wanted you to do is, and you can still do this if you want. So if I go back to geoprocessing, is to make a map that was the difference between each layer and the first IDW that you ran. So IDW minus spline 1, and run that. So you can see that this map is actually a difference between the two interpolation algorithms. So you can see really well the areas that are highlighted. Now, does the really dark areas represent bigger change, or do the really bright areas represent bigger change?
The bright areas represent bigger change?
Yeah. So it's kind of a trick question. Think about it a little bit longer. It's not the dark areas or the bright areas, it's both. Those values that are right in the middle, that are close to 0, are the values where there's very little change. Does that make sense?
Right, because 0 is your baseline, and then the positive and negative is how far from the middle.
Right. 0 means that the spline and the IDW were the same. So you can see, like in this area right here, the difference was probably pretty great because it's an area where all of a sudden there's no points. You know, there's no points right here either, but there's a whole lot of points around here and a whole lot of points around here. And so it was probably the spline algorithm that was more sensitive to trying to force itself into all these points, and it probably created a big ridge line right there. Let's see if that's what happened. So, so you see how these values right here, it's actually not a ridge line, it's a big depression in the spline. And that same, let me turn off everything, but yeah. So this depression that it created in the spline data set, because it was trying to force that rigid sheet, and it created a bow in the rigid sheet that went downward, exists here in the spline, but it does not exist in the IDW. See how it doesn't exist in the IDW? That's because it's not trying to force everything into a rigid sheet. It's just using the nearby points and it's averaging them. So that explains the difference between those two values, between those two interpolation techniques. This one and this one. So what that likely means is that these values were trending down and these values were trending down on this side, and so because they were both trending down, it bottomed out in the middle. Whereas in the IDW, it just kept averaging across. All right. So yeah, I don't know. You're free to put whatever 5 maps you want, but you need one map that represents each output, each of the rows in the table. I personally still think this would be a really good map to use, but this map is also going to show a lot of those differences. See that? Versus, so that's the spline, and this is the IDW. You can see how it changes a bit there significantly. So you could still point to this area as being an area that changed in your description. But remember, I don't want more than definitely less than a page. A paragraph or so should be fine, just describing the general areas that are changing more than the other areas. All right, and then finally, you are going to calculate IDW by hand, just so you get one more practice at understanding how this works and what it's doing. But you're only going to calculate it for a single cell, so you're not going to do what ArcGIS is doing, but you're going to do what ArcGIS is doing for every single cell. But you're going to do it for one cell. So you're going to do it for here, for X. And you've been given all the information that you need to do, that you need to have to interpolate the value here at this location. Okay. So you're going to determine the value of X, the value at location X, is probably a better way to say that, using the IDW interpolation algorithm with the neighborhood defined by M, okay, and R equals 2. Now, depending on which literature we're talking about, the R can sometimes mean radius, but here I'm talking about the weight. So just to be clear, that's the power of the IDW algorithm. Okay, so then you're going to do it again, but all you're going to do is change the R value to 3, the weight to 3. Okay. All right, so the way that you do that is you follow the example that there were a lot of slides in this lecture. You follow the example that we started with back here. Okay, see how the power is R up here. All right. Now this formula may look a little intimidating. People say, "Hey, I'm horrible at math," but it's actually pretty easy to set up. I can actually start that up. So there's 2 different ways to do it, and I went over both of them in the lecture here. But basically, we're calculating a weighted mean, and the weight is the inverse of the squared difference, and then the second time it's going to be the inverse of the cubed difference. So in this question, it's the inverse of the squared difference, and this question is the inverse of the cubed difference. So you're going to see how they change. Okay. So this one, everybody will get the right answer. Sorry, everybody will get the right answer. Hopefully, everybody will get the same answers, or should get the same answers. There is a correct answer for these two, because we're just talking about 1 point, and we're just talking about math. So Excel. So this is what I would do if I were going to solve this problem. I love using Excel for math problems rather than, especially multiple math problems, rather than just punching it all in on the calculator. So I've got 4 points, and these are the distances, and these are the value at that point. So in other words, that's like the lead value or the elevation value. Okay. So I'm going to put those all in there. I'm going to say values, and I'm going to say distances, and then I'm going to punch all those numbers in. So 3, 5, 5, and 6. 3, 5, 5, 6. I could even, just for fun, label D, C, B, A. D, C, all right, and then the distances are 2, 3, 2, and 4. And it does matter the order that you put them in, 2, 3, 2, and 4. They just have to match up. The right distance has to go with the right values. The order themselves, they don't matter. In other words, the 3 has to go with the 2 because this is 3 and that's 2. Okay. All right. So in order to calculate the weights, that's this this right here, the weights. In order to calculate the weights, we're just going to take 1 over the squared value. We can take, equals 1 divided by this number 2, caret, where's the caret? Above the 6. Caret 2. So those are all of our weights. So now we have our weights. And I actually cover this in the video. I talk about it in the video. So once we calculate all the weights, one option is to then adjust the weights so that they all add up to 1. Okay. So to do that, we take the total of all the weights and we divide those numbers by this value. So in other words, we could go equals the sum of these values, and then we divide equals this divided by the sum of the weight. Okay. And then so on. Equals this divided by the sum of the weight. And so on. Okay? That's one option. And then you have all these numbers, and they should add up to 1. 0.15, 0.26, 0.59. They should all add up to 1. Okay. And then you just multiply those by the first value. So in our case, it would be these numbers. In our case, it would be those numbers. So you multiply the values that all add up to 1 with those with the values at each point, and you get a number. And then you just simply take the average of that number. Take the average, sorry, not the average. You just add them all up. You add them all up, okay? That's one way to do it. These are just 2 different ways to calculate a weighted average. The other way to do it is to the other way to do it is like this, where you take each weight. This is the way that I usually do it, but I explained this way last. You take each weight, which remember it's the inverse distance, the inverse of the distance squared. Second time it's the inverse of the distance cubed. You just take each weight and you multiply those by the values. You add all those up, and you divide by the sum of the weights to get a number. Okay. I think that way is more intuitive. I mean, that's the way I've always been taught to calculate a weighted average. So you calculate the weights, you multiply all the weights by the values, and then you add all those up and divide by the sum of the weights, of the raw weights. They're going to give you the same answer either way. So it's good to go back through and make sure that you understand. But even if you just Google calculate weighted average, you will get an explanation on it. The only thing that won't help you with is calculating the actual weight. But the formula for calculating the weight is pretty easy. It's just 1 over the distance, either squared or cubed or whatever number goes here. The number here is the power, the R. That's this value here. Okay. Now in the formula here it says to the negative R. Why is that the same as saying 1 over d to the R? Well, that's the way math works. Is that d to the negative R equals 1 over d to the R. And so we were just implementing that here. So okay. All right, so I'll leave that there. You don't even need ArcGIS to do this part, and just include that answer. So you'll have you'll have an answer here, an answer here, and this should help you even more to understand what changing the radius value is, because that's the only thing, not the radius, the power value is. The radius is unknown, but we're just including all of these points. To show you what the power value, how the power value changes the result. So you'll see that that this one will weight the closer points in a greater way, and so the value will be closer to the closer points rather than the further away points. All right. I realize that I left my video up the whole time, which I don't think is going to be a problem, but I think it shows up in the corner. So the only weakness to that is it makes the rest of the screen smaller. So hopefully that still works. All right. Are there any questions? I know I said about an hour, and it was an hour and a half.
I don't have any questions.
On the Excel sheet,
yeah,
you just added A through D together for the one right below it, right?
I added these together Excel for that. Yep.
Right, and that's just okay. Sum, and then those, and then you pick like that one. Through that one.
Yeah, there's several ways.
Okay, yeah, I got it. I got it. I was.
I'm going to change this a little bit, so I'll delete these two. I think, in my personal opinion, I think the easiest way to do it, you still need this number here, but my personal opinion, you just take the weights and you multiply them by the values, and then you get the weighted. You get these values, and then all you do is add these numbers up and divide by that number. In my personal opinion, that's the easiest way to do it. And so this version is what I'm doing on this screen right here. So slide 74, I think, is the easiest way. That's the way it works for my brain. But they're all equivalent mathematically. It's just when you want it's when you want to divide the weights into the overall value, but you can do it at different times in the equation.
Dr. Raber?
Yes.
So I didn't see where you use the R equals 2 versus the
Okay. Yeah. So
where R equals 3 is going to go?
yeah. So that was right in this formula right here. You see where it says to the power of 2, you would change that to 3.
I see.
So the way, like, if you wanted to make this easy, like, so that you could just adjust it, you could say power, and then 2, and then just change this to that value. All right. And then once you get the right answer, you can just change all these to 3.
I see. Okay.
Yeah. So yeah, you're right. I didn't like make that obvious. Now IDW doesn't let you change the power individually to each point, but but that's, I mean, that's in a way that's kind of what's going on with some of the other interpolation algorithms. But IDW keeps that value constant. But theoretically, you could do that. You know, in some areas, you could weight, or not so in some areas. For some points, you could weight them higher than others. But you know, that's not what IDW works. So when you change 2 of these to 3, you're not going to get the right answer until you change them all to 3. If you do it that way, that's what I'm trying to say. All right. Any other questions?
On column 4, you said those are all supposed to equal 1?
On problem 4.
I mean, not for problem 4, on column F.
F. F? No.
Yeah,
So
column F all supposed to equal.
Sorry. So I switched. So there's 2 different. So this is the normalized weights. So let's see what it calls it in the lecture. I forgot. So there's 2 different ways of doing it, Ben, and I kind of switched the adjusted weights. So the adjusted weight is equal to this divided by that equals this divided by that equals this divided by that equals this divided by that. Now these should all equal 1 if I do it that way. See, those all equal 1.
Oh, okay.
But then the reason why I think this is harder is because you have to add another column here that multiplies all the adjusted weights. That's what's happening here. You take all the adjusted weights. Let's go down here. You take all the adjusted weights and you multiply them by the values. So you have to take this value and multiply it by that value, and then you add all those up and you get the answer. So basically, going this way, you're doing 4 division problems. And if you just sum all these up, you're just doing 1 division problem.
I got you. So for our assignment, we only need our totals from our weighted times values for each letter.
Well, it's just 2 different ways. You're going to get the same answer, hopefully. You should get the same answer either way you do it.
I guess that's what I'm confused about is the adjusted weight and the weight times values, they're different.
They're different. They're just 2 different ways to solve the problem. So slide 69, 70, and 71 and 72 demonstrate the adjusted weight method of solving the problem. Okay, slide 74 demonstrates the weights times values method of solving the problem, but they give you the same answer.
Oh, okay. That makes sense.
It's a
That's
little
what
bit
got
more
me
clear if you
confused.
watch the video because I say that same thing.
Well, I had watched it earlier, but
Yeah,
I didn't fully understand then what I was watching
right.
because I couldn't ask questions to the video.
Right, exactly. But if you go you can review the video. But if you still have questions,
Right.
please ask. Uh, but yeah, these are two different ways. So the adjusted weight here is from the first slides. This is from the second slide. They're solving the problem uh, different ways. So in the adjusted weights version, you're taking each weight and dividing it by this. In the weights times values time, you're multiplying the values times the weight, and then when you get to the total, you're going to take that total and divide it by this. Just one division problem.
I got you.
If you do the adjusted weights, you're taking each weight and you're multiplying it. You're dividing it by this value, and then all you need to do is add them all up at the end. It's basically when you choose to do the division problem is the difference between the two versions. So although I think this one makes sense more intuitively in Excel, computer scientists say that this one is faster because it only requires a single loop through the data.
I got you.
But mathematically, they're equivalent. All right. Any other questions?
I don't have any more right now.
Okay. Well, Charles, I have that appointment with you at 9:30. But if anybody else has questions, let me know. I will be away from my computer tomorrow for much of the day.
Dr. Weber, I had a
Yeah.
quick administrative question.
Sure.
I was wondering if you were going to be posting any of the grades for the previous labs anytime soon, so that we can kind of judge where we're at.
I need to get caught up on that. So yeah, that's a good point. I'll get those posted.
Okay, thank you.
All right. Any other questions?
Nope, not for me.
All right. Well, I'm going to go ahead and stop the recording.